Okay, so what we have seen so far is, well, we have derived the general expression for the kth order correction to the energy and the eigenstate of our Hamiltonian. And just to get the kth order correction, we just need to know the k minus 1, k minus 2, and so on order of corrections. We have derived the 0th order correction, the 1st order correction, and the 2nd order correction. As you see, the 2nd order correction for the wave state, wave function is actually pretty long. For L different from n, but we also need to add this Cn term, which we have not been able to do, because when we take the inner product with phi n, this term just disappears. The same happens for the first order. So this expression will have to be a bit longer if we impose our normalization condition. So how do we find it? Well, to find it, we can obtain an additional equation. We can say that this is equal to 1. We normalize our wave function. And by normalizing, what we mean is that the norm, which is defined as the square root of the inner product with itself, is 1. And this implies, if and only if we take we square both sides, at this, the inner product with itself has really just got to be 1. So this is the condition we're going to impose, and we'll see that we will be able to get Cn1 and Cn2, and actually Cnk. So let me just do it. So our general method would be to, just as a quick recap, to take the inner product with phi n, then take it with phi l, different from n, and then apply a normalization condition that we'll derive now to obtain the Cn term. So let's just do it. Well, just really quickly, recall that this is, we are assuming a power series expansion like this. This is what we are assuming. If we take the, the inner product with itself, we will have this series expansion, but taking the bra of it. The complex conjugate of lambda is just lambda because it is a real number ranging from 0 to 1. This is okay. And this lambda. Well, k goes from 0 to positive infinity. Now, we can apply the Cauchy product, this one right here we have used previously, if we consider that both series converge. We're assuming that they converge and that one of them is absolutely convergent. So we are going to assume this. If this does not hold, then we will have to find another method to do it, or I don't know if we could even be able to do it. You can try to multiply term by term, but I don't know if maybe you will run into some problems. So, yeah, if we apply the Cauchy product, this rule, we get that this is just the sum from k equals 0 to positive infinity of the sum, yes, going from L0 to k of AL, in this case it will be this one, so we just replace k by L, so we just get L times Bj, raising j by k minus L, just replacing well, we can write it like this if you want to, so you can see it better. This I just use a different dummy variable here. And see, this is Bj. So B, k minus L, is just replacing j by k minus L, so we get k minus L n times the power of lambda. What we are doing is we are imposing that this is equal to 1. Now, I just want you to notice one thing, that is if we consider the zeroth term here, we expand it, we can write this. So instead of 0, I'm going to write a 1, and I'm going to expand the zeroth term. The zeroth term is just the sum going from L0 to 0, so it's just 0, L is just 0, and K minus L, K is 0, L is 0, so it's just 0. Times lambda to the zeroth power is just 1, so that's it. We know that phi psi 0 n is just phi n 0, so we will just write phi n 0 and phi n 0. And we're posing that this, all of this, remember that we changed the sign from 0 to infinity to 1 to infinity, and we're taking out this term. So we're posing this is equal to 1, but this is equal to 1 because we are working with an orthonormal basis. So really, this condition just means that all of this has got to be equal to 0. And for it to be equal to 0 for all values of lambda k, we need that this coefficient term, this term here, is 0. So the normalization condition, let me just put it here, can only hold if this holds, if this is 0. Okay, so this is our normalization condition. We need that this coefficient is always 0. So this is the general condition for k greater or equal than 1, because for k equals 0, we already know absolutely everything. We know that in that case, all the CLs are 0, except Cn, which is 1. So this is the general expression for k greater or equal than 1. So let's particularize it for k equals 1. So for k equals 1, the sum is going from 0 to 1, so we just get 0 for the correction times 1 minus 0 plus the first order correction times 1 minus 1 is just 0. And this has to be 0. Now, notice that phi 0, that psi 0 is just phi 0, as we said, and that phi 0 is just phi 0, as we said. And this is just 1. We said in other videos that times this, it just picks out the nth component. So we get this. And likewise, if we take the complex conjugate on both sides, this just takes out again C and K, but it's complex conjugate. This is what we have. So really, this term right here is just the Cn component of the first correction plus the Cnth component conjugated of the first correction. This is a condition for C1 to hold. In general, Cn1 is a complex number, so we can rewrite it as A plus Bi. If we add it to its conjugate, just remember that its conjugate is this, we get that this expression just reduces to 2a equals to 0, that is, a equals to 0. This just means that our C1 has a 0 real component, so this is just 0 plus IB. And we're actually free to choose the value of B. This will just result in a different phase, but all the physics and everything behind it is really just the same. Just if you remember from problems in quantum mechanics and theory of quantum mechanics, we are usually free to choose our wave functions up to a general phase. So this is where it comes from in this case. And why not choose our phase such that this is 0, right? So we will choose b equals to 0. And yeah, that will be it. Yeah, we will just choose b equals to 0. And in this case, Cn1 is equal to 0. So this is what we get. Just notice, again, let me just do a quick recap. From this condition, we got that the real part of Cn1 is 0. It has to be 0. So C1 in the complex plane can only be a number, an imaginary number, okay? It's IB, so it can be anywhere in this vertical imaginary axis. So we can get any of these numbers in this imaginary axis, and everything will still work out fine. So if we can choose any number, why not choose 0 to make our life easier? So that's what we will do. So we will choose the imaginary part being 0, so Cn1 is in general, well, is in all just 0. So this is it. And just, I added this before, just to say that psi 1, the first correction, is just the sum of the n different from n corrections plus this Cn1 correction that we didn't know. But we already know it now, so you can just get rid of it and say it's 0. So let's go on for the second order correction. We will do the same procedure and see what we get. Spoiler alert, in this case, it's not 0, it's actually a bit longer the expression, but well, that's just how life goes. So for k equals 2, we get the sum going from 0 to 2, so let's just expand it. 0 of order correction, 2 minus 0 n plus the first order correction times 2 minus 1 plus the second order correction. And this is 0. Again, whenever we have this 0, we just write this, because we already know, we derived it. Second order correction, first order correction, really? Right? Yes? And zeroth order correction, just phi 0. Once again, when we have, I'm going to repeat it just so you don't get confused at any point. This just picks out the C and K component, where K is just depending on which correction we're doing. And this is just the complex conjugate of this expression. Okay, just remember that in general, the coefficients C and K are complex because we're working in a complex Hilbert space. Okay, the body of numbers that we're working with is complex. So, well, then just write Cn2 plus Cn2 conjugated plus this times this. So you could be tempted to say that it is 1, but we don't really know if it's 1 or not yet. So let's just express it like this. So what can we do? Well, we can say, again, if we express Cn2 as a complex number, when we add the complex conjugate, we will get that we only get 2a, the real part of it. So if this is 0, this just becomes 2a plus this. And And the reason I said that you could be tempted to say that this is 1 is because we have always been working with orthonormal basis phi n, but the thing is that we are imposing that the whole psi n is normalized, but this can maybe not be normalized, and psi 2 can maybe also not be normalized. In fact, they won't be normalized because otherwise we will something wrong. We'll see what the expression is. But what I was saying is that just like before, we get this. In general, we have that Cnk plus Cnk complex is just 2a, where a is just the real part of Cnk. This means that we can choose bk, let me just write k here, equals to 0. That is, the imaginary part is equal to 0 always. Okay? So this is our choice. We want to choose that C and K is just a real number. So let me just write it here. And we can do this because it doesn't really affect our equations. We will choose that C and K is just equal to AK belonging to the real numbers. Again, what we're doing is just saying that its imaginary part is 0 because it doesn't affect our equations. Now, yes, so with that condition, A really is just Cn2. So what I'm saying, if Cnk is equal to AK, Cn2 is just equal to A2. So all of this is just really 2A2. Let me just erase this, and we will get the following. Oh yes, what I'm saying, let me just erase this, is from all these arguments, Cn2 is a real number. So if it is a real number, Cn2 is equal to its conjugate. So we get is now Cn2 is equal to minus the inner product of the first order correction. And in general we get this. So this is what we have. Now what is this? So let me just do this. I'm sorry if I'm making you confused or anything. It was fine. Everything was fine. So if we express, we can calculate this in two ways. So we can say that phi 1n is just equal to the sum, as we said before, from n different from n of Cm1 phi m0, this one just stands for the first correction, and m is just a dummy index. We can take the inner product with itself, or we can just say that if we express it in matrix notation, we'll get a really nice answer, a really easy answer. So if we express it in how do I do it? I don't know what's more instructive, if to do it by the product or by matrix, but look, let's just do it by a product, okay? And maybe afterwards we'll do it by matrix method. What is this really? So this is just the sum from n different from n of of Cm1 Im0 times different from n Cm1, and really this should be the complex conjugate. In general, we don't know if this is complex or not. So we don't need the complex conjugate here, because this is m different from n. Okay, it's no longer Cm. We get this. So just think of it term by term. If I expand the first term here, it is gonna make all of this zero except for the term that is equal to it. Likewise, if I expand the second term, it's gonna multiply all of this and make it zero except for the second term. So all in all, we get that the only terms that survive are the terms that are equal between each other. So we will just get C1 complex conjugated, Cm1, and this is just the sum over all m, different from n, of Cm1 squared. Another way to see this, using our Dirac notation, is to say, okay, in my basis of a H0 Hamiltonian, well, this is basis, we can express this as a column matrix with Cm1, Cm2, and so on, so to whatever number we want. So these are the components of each element form matrix of 510. The ket, the bra, is just this transposed conjugated. So with this conjugated, and so on. Let me just erase it. If we multiply these two, we just get a matrix multiplication. This times this is just Cm1 conjugated Cm1, that's Cm2 conjugated Cm2, plus so on, so on, so on. And this is the sum over all values of m. But what about m equals 0? Well, it is going to be somewhere here. M equals n. Complex conjugated. Cn1. Sorry, it's a 1. I was writing too tight. When we get to this term, right here, we get Cn1 conjugated times Cn1. But we said, we tried before, that Cn1 is 0, or we have chosen it to be 0. So this just goes away. So we can sum over all m, having it out that Cn is 0, we wouldn't even have to sum over n. So when n is not n, we get, yes. Sorry, this is one, and what I'm saying is that the first m, the second m, and so on. The first component, the second component, this is still the first order. The first component, second component, first component, second component, and so on. So sorry about that. So what we have is the sum over Cm of 1 conjugated Cm1. And this is just, as we said before, G modulus squared. So really, what we get here is another sum from m different from n of the modulus squared of the first of the correction of the components of the first order correction to our wave function. So this will be it. I'm gonna just write it here for completeness, and we'll do a quick summary of non-degenerate time-independent perturbation theory.